Hello, everybody. Welcome back to Calculus. In section 3.4, we are going to be talking about derivatives as rates of change. Now, we have been differentiating functions, of course, but what do you use functions for? Okay. One of the important applications of functions is to describe change, like the position of a flying object changes, the price of something changes with respect to time, the population of a certain country or a certain animal changes with respect to time. And so the derivative naturally describes the rate of change of these quantities. And so we are going to look at a couple of examples of how the derivative can be applied as rates of change. The derivative can be applied to be interpreted as the rate of change of the quantity that f is describing. So let's get into it. Our section 3.4, derivatives as rates of change. All right, so this is going to be a short section, and we are going to be describing derivatives as rates of change. And so many times a function can be representing some quantity that changes with respect to time. Now, because we are talking about time, this x could be easily rewritten as t, and in many situations we actually do use f of t. But since we have been using f of x, where x is the independent variable, let's let x this time represent time t, even though I write x. All right. Now, we have this point a, and of course, the value of y is f of a, whatever that is. Okay. And then we have this point f of a plus h, right? And this function is increasing from this point to this point. And that rate of change, or not the rate, but the quantity of change is what we call the rise, or delta y, right? And we have an easy description of that as a mathematical or algebraic expression. It is the value f of x, f of a plus h minus f of a. Okay. Now we call this the amount of, well, this is the amount of change. More technically, we call this the absolute change. Absolute change have to do with, as opposed to the relative change, which is the percentage increase, right? So this is actually the difference in those two quantities, two y values. No problem here, right? And if you take that and divide it by delta x, which is of course just h, we have, as we have studied, this is the difference quotient, or we can call this the slope of the secant line connecting a and a plus h. Also, this is the average velocity, right? Average rate of change in the interval from a to a plus h. So we have studied all of these things. Now, if you take the derivative at a, this is the limit as delta x goes to 0. Okay, which is of course, what we denote as dy dx, all kinds of equivalent expressions here or symbols, but it's really just the limit we talked about before as we defined what the derivative is. All right, so this is the instantaneous rate of change. All right, so those are all things that we have studied before. All right, now in this case, we are not told what f is, but if f of t is the position, or maybe the distance traveled, okay, but it's a position on a linear, something that's moving linearly, along a line, say the number line. If ft is the position of the object, f prime t, which is the derivative, it's the instantaneous rate of change of position. We know this better as the velocity. Okay. Now the velocity could be positive or negative. Okay. Typically, if you are talking about the a linear motion on the real line, this is the positive direction. This is the negative direction. Why is it? Well, just because somebody said so years ago, and everybody decided to agree that the right movement right motion is the positive direction, and the from right to left is the negative motion. But if you ignore that, if you just take the absolute value of the velocity, regardless of which direction you're moving, this number is called speed. Okay, so this is, this is the first derivative. I guess I said I was going to use x as an independent variable, but t could easily be our independent variable. That's fine here. All right, and so what happens if you take the second derivative? This will be the derivative of the derivative. And so this is how fast t, the velocity is changing. So we call this, I said this before too, but this is the acceleration. We write this as d square y or f over dt squared. A strange symbol indeed, but that's how we denote this. Okay. All right. Now I am going to say one thing that I did this before too, but the book also has this again. So this is a sort of a simple rough sketch of what's happening here. You remember how we drew this tangent line to this point? Oops, that is not a very linear thing. So maybe I should draw a tangent line more carefully. Yeah, so this is a tangent line. Okay, it's hard to see. All right, maybe I should make it a little thicker. There you go. All right, so this is a tangent line. Okay, assume that this point is the only place where the line touches the curve f. Okay, so this is the tangent. Tangent line at A, okay, to f. All right, now if you pick a point here, let's say this point is very near A, and again, I'm exaggerating the distance between A and A plus H, which is of course H, just so you can clearly see what's happening here. The actual difference is what we call delta y, right? That's the rise. But many times, especially if H is really close to A, basically, anytime you see a smooth curve, if you zoom in closer and closer to this point A, okay, eventually a curve like this, if you focus on this and then smaller and smaller section, basically it all becomes very much like a line. So any smooth curve taken extremely in small portions is going to be a line. And so the tangent line gives you a nice approximation of what the function value is near A. And for that approximation we use, in fact, this is called linear approximation because we are approximating f by a line, the tangent line. This is called dy, okay? And I use this, remember the distance h is also called dx. And the slope of the tangent line is f prime. And so the slope of f prime is dy over dx. I should not say the slope of the f prime. I should say f prime A is the slope of the tangent line, which is dy over dx, right? So dy can be written as the derivative evaluated at that point times dx. Okay, so that is fine. That's no problem. This thing is called the differential of f at the point A. And the point is, no pun intended, as I said, when h is really small, dy can be used to approximate delta y. Now, delta y can easily be calculated by the formula we had right here, right? So why bother? I mean, why bother to approximate this? Well, in the real world or in real world applications, many times we don't even know or are not given the equation for f. Maybe all we know is f of a and the derivative at f of a. And we are not given an explicit equation for f. In that case, you can't find what f of a plus h is because we don't have data. And in that case, the best we can do is to use this linear approximation. All right, so f of a plus h is, of course, f of a plus delta y. You just add this change from f of a to this new point, but this can be approximated by dy, plus dy. And of course, dy is f prime of a times dx. And so when you do this, it's called linear approximation. Okay, now this is a subject of section, I think it's 4.2. So no, yeah, section 4.2. So we will not worry too much about it at this point. But again, just to remember later that we will be using the derivative to approximate the value of the function near the point where we evaluated the derivative. All right, back to our motion illustration. And this is, by the way, an example in the book. It's called 336. Okay, so what we are given is this linear motion, which means some object is moving back and forth on this line. And you have 0 and 4 turns out to be an important point here. You will see why in a moment. Okay, and an object is kind of moving back and forth, like going up, going back and forth, maybe, maybe changing the directions a few times. And that position is explained or described by this cubic equation, t cubed minus 9t squared plus 24t plus 4, where t is non-negative. Now t starts at 0 because that's when time begins with respect to this experiment or this motion. All right. Now when s is equal to, when time is equal to 0, you plug in 0 for t and you basically have 4. So this is a starting point. Okay. Whatever this object is doing is going to start at the position indicated by this number 4, and then it starts to move. Okay, so let's find the derivative. Part A says find the velocity of this function at any given point t, and of course v, the velocity, is simply the derivative of s, and now we can quickly differentiate this, right? 3t squared minus, now 9 times 2 is 18, t, 2 minus 1 is 1, so the new exponent is 1, and then 24t just becomes 24. 4 disappears altogether because it's a constant. Okay, so that is the derivative, no problem. All right, part B of the question says find t where the motion stops. Actually, the problem says where the object is at rest. Okay. Now the object actually comes to rest when the derivative is equal to 0, right? When the velocity becomes 0. But it happens like, at just moments. Okay, it doesn't stay at rest for a long time, and as you can see, it only happens at a couple of points in time. So find t where the motion stops. And so this is basically asking, when is the velocity equal to 0? That's the question. Well, we have this nice equation for the derivative, which is a velocity. So we set that equal to 0. Now this happens to be a quadratic function. Taking out 3, you get that. And of course, you can just divide this by 3 because 0 divided by 3 is also 0 on the right-hand side. Can you factor this? Sure, 2 and 4 would easily do that, -2, -4. And so this is equal to 0, meaning t is 2 and 4. Okay, so it appears that only twice in the throughout this motion of the object would the object come to a stop, and in both cases it comes to rest, and then instantaneously it's going to start moving again, right? But this happens at 2 seconds and at 4 seconds. All right, now we have no clear indication of which way it's moving and so on, right? So let's ask that question. So when is the motion to the right? And so for which t is the motion positive? And again, if you look in the book, the example in the book, it doesn't talk about the positive motion, but I am defining a positive motion to be from right to left. And when is it negative, which means left to right, okay? And so how do you know this? Well, we have already established this is 0, it starts at 4, and I don't even know which way it starts to move. Would it start moving this way or that way? That depends on the velocity at 0, right? So these are the questions we're going to ask. But well, that's a good point. Let's say here's the velocity. In the factor of the 4. Okay. Can you tell where this is positive and negative or equal to each other? Yeah, so this is one of those questions that you probably, this is a type of question that is typically presented in like a class like in Algebra 2 or intermediate algebra, and some students hate this. Okay, this is a way to do this. So all right, so this expression becomes 0 at 2 and 4, right? So these are the boundary points. If the sign changes, it would change at these points. Okay, so let's go ahead and think about this. T minus 2. Okay, T minus 2 is negative here when T is less than 2. If you are confused, just plug in any number like 1 or 0 or -1 or something. If you subtract 2 from these numbers, the answer is going to be negative. Now, when you plug in 2 for T, then this will become 0. Now, any number between 2 and 4, such as 3, will make this positive. 4 minus 2 is, of course, positive. 5 minus 2 is, of course, positive. So as far as this factor is concerned, T minus 2 is going to be negative here until you get to 2, where it becomes 0. And after that, forevermore, it's going to be positive. T minus 4, the second component or the second factor, is negative here. Even when it's 2, it's negative. 3, it's negative. 3.9, it's negative. 3.99, it's still negative. But as soon as x or t reaches 4, it becomes 0. And after that, it just turns positive. 4.1, 4.2, 4.3, 5, 7, whatever. Minus 4 would always be a positive number. All right, now the velocity is 3 times these two things. Now 3 is a positive number, not changing the sign of it. So you basically have negative times negative here. That's positive. 0 times negative is, of course, 0. Positive times negative is negative. 0 times positive is 0. Positive times positive is positive. Okay, so, and by the way, this kind of sign chart, if you are not familiar with that, you may want to review, and maybe you can look up, sign charts in math or something, sign charts in algebra. This kind of analysis is going to be quite important because many times we want to find when the derivative is equal to 0 or positive or negative. Remember, when the derivative is positive, that means the function is increasing. In this case, in this context, it means it's moving this way. If the derivative is negative, it means the motion is this way, or typically it's decreasing. The function is decreasing. So when we ask later things like when is the function increasing or decreasing, or it hits its highest or lowest points, sign charts are what you will need to draw or to construct in order to answer those questions. Okay, so that means the velocity is positive. And where? Right here? From, well, it starts at 0. And then 2. And then from 4 to infinity, right? Not including 4, because at 4, the velocity is 0. It's negative in where? It's only this part between 2 and 4, open interval, not including 2 or 4. And the velocity is, of course, exactly 0 at 2 and 4. All right, so now we get a good picture here. Oh, by the way, let's try to find out t. We already found s of 0 is 4. Okay, now the position function is actually, where are we? It's way back here, right? So all you have to do, and I'm not going to do this right now, you can do this easily. All you have to do to evaluate this function at 2 and 4 is to plug in 2 and 4. So when you plug in 2, you get 24. Okay? And when you plug in 4, this is like 64 minus 144 plus 96 plus 4. Anyway, if you calculate this, you can easily compute the answer to be 20. All right, so now we have a good understanding of what this motion looks like. All right, the motion is kind of hard to describe on a piece of paper, but since I can talk my way through this, I think it's going to be okay. All right, so if this is 0, it starts at 4, right? And 20 and 24 are going to be a pretty important, each of these is an important point. So what's going to happen? The object starts right here when t is equal to 0. And it looks like from 0 to 2, that's this area or this interval, the direction is positive because vt is positive. The velocity is positive, meaning it's going to start moving this way for 2 seconds. And right at 2 seconds, when the position is 24, so it's going to go from here, takes off, takes off, takes off. And within 2 seconds, it's going to land right here at 24. And at that point, the object stops and changes its direction until, just for 2 more seconds, okay? Until t is 4 and the object is at 20. And at that point, the direction changes to positive again. So remember, it starts here and goes to 24 in 2 seconds. And in the next 2 seconds, for the next 2 seconds, the object goes from left to right, just for 4 units. And when the object hits 20 at t is equal to 4, it stops and then starts to go backwards or to go forward in the positive direction. And it'll be forever going in the positive direction. So the object is going to move like this, in a sense. Okay. Now, if you graph this function, it starts at 4, okay, and it goes to 20 and 24, and basically it's going to go like that. Oh, goes like this. That's a bad picture. Yeah, it's ugly. Start from 4. It starts to go like this, and oops, no. It's a cubic function. You know what? I should draw this nicer. Okay, so give me just a moment. Okay, this is much nicer. So the object starts at position 4, and it starts to take off, okay, in the positive direction up until when t is equal to 2, when it hits 24. So it goes up, and stops here, changes its direction, starts to go in negative direction. Well, let's see, slowly moving backwards, sort of like this. It's always smooth, and it hits t is equal to 4. It doesn't go down this much, right? T is equal to 4 when the position is 20, right? And then it starts to go up again. So, and it's going to go up forever like this. Okay. So, and this is a typical cubic function, which is good because we started with a cubic function. Where are we? Yeah, that is a cubic function where the leading coefficient is positive. So you knew that the end behavior is like that, which is consistent with what we are seeing. And so that describes what the motion is like that is described by this position function. All right, so get familiar, get used to finding things like the velocity and the acceleration and the direction up. When is the function going up, down, increasing, decreasing? Because these are the questions that we will be asking probably for the next few weeks as we study or as we continue to study differential calculus. All right, so that's it for section 3.4. I will see you later.